Yep, I think we're recording now. And yeah, hopefully you can see the screen easy enough. Yeah, so the problem was, by the way, can you see my screen when I screen share?
Yes.
Great, okay. Still going off my computer here, so my laptop, so things are just a total mess. But if we basically have a vector y that we want to express as u and like v is equal to, some vector orthogonal to u, um, well, just visually what we're doing here is this is a 2D plane, right? Because we're dealing in two dimensions. Two dimensions. So u might look like, what's up?
Very good.
U kind of looks like 1/6, and y is 2/6, I guess. So basically, the idea here is that u is just going to span, I guess, a parallel line to u. And then if we can just come up with a vector orthogonal to u, I don't know, let's call that v, we should really just be able to express y as some linear combination of u and v. So the problem really comes down to just two steps, right? First is find v. And this is pretty simple to do. This is, wrapped up in the language of linear algebra, but we've been doing this since middle school, right? Uh, how do you find a vector orthogonal in a 2D plane? Well, if u has slope, oh, I'm sorry, u is 6, 1. My bad. So I didn't draw it right. So it's more like this. U is, u has slope 6. So then to find something orthogonal to it, you're just going to do a slope of negative 1/6, right? Just take the negative reciprocal.
Okay.
So v could just be something as simple as something like that, right? And just as a sanity check, if you take the dot product of these two things, you ought to be able to verify that the dot product of u dot v is equal to 0. And that's our condition for orthogonality, right?
Right.
So now that we have u and we have v, and by the way, of course, we could take v to be like, it's not unique, right? It's only unique up to a scalar multiple. So this could have been negative 2, comma 12, for example, right? But I digress. Now that you have u and v, you want to be able to express y as some linear combination of c1u plus c2v. And yeah, how would you do this?
Plug in what we know to u and v, and then like make a system of equations with it, or not?
Yeah, I mean, you could definitely do that. That's exactly right. But how would, in the language of linear algebra, or maybe the, terminology of linear algebra, how would you do this? I would probably do this by saying, like, we're trying to solve for C1, C2 in an equation where, what does this look like? This is U and this is V, right? So this turns into C1U plus C2V is equal to Y, right? And U, V, and Y are all perfectly, we already know those. We're just trying to solve for C1, C2. So you could basically, like, just take do reduced row echelon form and take the inverse if you want. If that's too complicated, then you can always resort back to middle school methods and whatnot, right? But once you have something like this in linear algebra, you should be able to solve for C1, C2 one way or another, right? If
Yeah.
everything else is known.
Okay.
Does that seem reasonable? I think hopefully once you get to the, once you set up the final thing, things should be reasonably cookie cutter. But just doing this initial interpretation of trying to figure out what the heck the problem is talking about is admittedly a little bit confusing for this one. I don't know why they have to call it a span of U as the sum of a vector and span U. Yeah, I mean span of the sum of a vector in span of U just means like U with some constant scalar attached to it, right? So you end up maybe it ends up being a half U or 3U or something like that. But yeah, that's all that problem is asking.
Okay.
Hmm.
Do you know what orthonormal means?
Yeah, sure. So like orthonormal is really
So we
just
were
the
just
sum of its parts. It's when you talk about an orthonormal set of vectors. Let's say call it v1 dot 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 vn. It means that every single one of these vectors is orthogonal to each other, right? So for any given vi dotted with vj, the result is equal to 0. For posterity's sake, I'll draw the vector symbol on top. So for every I comma j that you can think of, the dot product is 0. That's what orthogonal means. And then the normal part just means that every single one of these things has length 1. So vi is equal to 1. And the reason we like orthonormal bases is just that they're really convenient to work with, right? So like your standard, x, y, z plane, using unit vectors, right? So using unit vectors with length 1, 1, 1, 1, we would consider that a orthonormal basis. Make sense?
yeah.
And a lot of the
Okay.
times when being asked to find a basis, you're sometimes asked to find specifically uh, an orthonormal basis, because intuitively, like if I gave you like this this vector, and like that vector, like yes, that would span the XYZ space, but somehow that's just a little bit messier. And like we as humans would prefer that it would be, prefer something nice and clean, like the XYZ unit vectors. That's all.
Gotcha.
Yeah. Oh, sorry. We usually call this I hat, J hat, and K hat, right? That's the language we usually use for multivariable calculus. Ringing a bell?
Yeah.
Yeah. Um, I'm sure there are like more substantial reasons that we like orthonormal uh, vectors, orthonormal basis vectors. Maybe revisit that topic in your book. I'm, sometimes you might have situations where, um, maybe they're really special and can get you something. But yeah, or help you solve some
So
problem.
there's a hold on, let me just share it. Because that makes sense, right? But like an orthonormal matrix then with orthonormal columns would just mean that it spans everything like you were saying?
Um, I think so. Um, so that's basically like saying you have a matrix that looks like this, right? An orthonormal set of columns.
Okay.
Um, I intuitively I would say yes, unless it was trying to be a trick question. Um, let U be a square matrix with orthonormal columns. Explain why it's invertible. Um, orthonormal columns. Yeah, yeah. Okay, gotcha. So never mind about the trick question. I was worried about the case where like v1 and v2 were the exact same thing, but then I realized that that can't be orthogonal. So when you have a square matrix, uh, like U, so that it's n by n, and that all these things are orthonormal, right? Um,
Right.
let me think about. I'm not exactly sure which set of theorems is like the fastest way to prove this, but intuitively, if it's orthonormal, that means that there's some linear dependency going on. Or sorry, linear independency going on rather. Um, shoot. So how would we prove this? So
Because
if we know that, what's up?
once it's inverted, it should be
Well, we're
what?
trying to prove that it's invertible. That's the result we're trying to get to, given that it's orthonormal. In fact, I don't even know if you need the normal part. Um, but what we do know is that, vi dotted with vj is equal to 0 for whenever I is not equal to j, right? So any two, the dot product is 0. So let's try to think about if we can use this fact to guarantee that there are no non-trivial linear combinations. Excuse me. So basically, we're trying to ask ourselves if, C1 V1 plus C2 V2 dot 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 with C n Vn, we're asking ourselves, can there be a non-trivial linear combination, such that not all the C's are 0, such that this total thing is equal to 0? And are you familiar with the idea of proving by contradiction?
As in, like, it doesn't do this, so then it has to do this.
Yeah, I guess that's a very, I guess that's a way of saying it. Um, sometimes it's just argue, we want to prove that given that it's orthonormal, we want to prove that it's impossible for this to equal 0 for non-trivial C's, right? And to do this, let's maybe start by saying, okay, suppose it messed up and was equal to 0, right? Could we um, suppose for the sake of contradiction that we had a non-trivial linear combination? Could we sort of reverse this logic, so to speak, and show that this must have resulted in a um, or rather, let's say, sorry, can we reverse this logic and you know disprove the original assertion? Sorry, I'm missing this really, really poorly. But the idea is, if you want to prove that it's not equal to 0, one way to examine this is to say, okay, let's say it's equal to 0, and let's see if we can make it really absurd, prove something really absurd, right? And I think the way to do this, can we dot it with itself?
Yeah.
Yeah, that's the trick, right? Um, what we could do is we could square both sides. And if we squared both sides, we would get something that looked like C1 squared V1 squared plus C1 C2 V1 dotted with V2. Sorry, when I say square both sides, I'm essentially saying take this and dot it with itself. If that makes sense. Um, does that make sense?
Yeah.
Yeah. So what I'm gonna end up getting here is that Oh god, there's got to be a cleaner way to do this. Um, so I'm almost like when I'm drawing it out like this, I'm almost arranging it like a matrix, but V1 dotted with V3. But you can kind of see that like it's all just one. Sorry, C2, C1, V2 dotted with V1. Like, do you see how I'm just like sort of adding all these up? And then the diagonals are basically the things like V3 dotted with itself, V2 dotted with itself. Like, are you kind of seeing
Yeah.
the structure of what I'm drawing out here?
Yeah.
Right? So I'm sort of claiming to you that because we know that V1 dotted with V2, sorry, VI dotted with VJ for I is not J, right? When that's going to be equal to 0. So all the off diagonal terms are 0, or rather the 0 vector. Right?
Sure.
But then
So
all the terms in the middle here are the ones that survive. And we know that this entire big sum is equal to 0. Does that make sense? Because I'm just
and
taking
we know that
I'm taking this original statement, right? And then I'm
yeah.
saying, okay, let's, for the sake of contradiction, let's say that this linear combination is equal to 0, and then let's just square both sides. And then squaring, for vectors essentially means taking the dot product with itself. And what I'm telling you is that only the diagonal terms on the left-hand side are going to survive. The ones where like VI is dotting itself, right? And all the cross terms like V1 dotted with V2, V1 dotted with V3, those are all going to die out, right?
Yep.
So then we get this result where C1 squared, V1 squared, C2 squared, V2 squared, dot, 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 all the way adding up to Cn squared, Vn squared is equal to 0. But this is absurd because all these terms, at least one of these terms has to be positive, right? Because all of the Vi squared, V1 squared, V2 squared, V3 squared, um, because we know that it's orthonormal, right? Any Vi squared dotted with itself is equal to 1. So this basically means that C1 squared, C2 squared, C3 squared. Do you see that? So like every single one of these things is a 1. Is a 1. So this is basically claiming that C1 squared plus C2 squared, all the way adding up to Cn squared, is equal to 0. But this entire case was assuming that this was a non-trivial linear combination. Okay, let me reword it. Let me say that's I'm sorry. I'm trying to think of the best way to word it. I'm Maybe I should not have used contradiction. Maybe I should have just done a more straightforward proof.
I think I kind of get it then. So
Do
would
you
you
see what I'm
say
getting?
that
Yeah.
like, the columns are orthonormal? We said, right? So then, since it's non-trivial, they all have to be non-zero.
At least one of these has to be non-zero, right? The fact that we assume that there's a non-trivial linear combination, non-trivial linear combo.
Which makes them linearly independent, right?
Non-trivial linear combination means not linearly independent. So I know that we're kind of shifting the logic around a little bit, but I'm trying to prove that this equality is not true, right? And to do that, I start by assuming that it is true, that there is a non-trivial linear combination that achieves equality. And then I need to show that this results in something absurd. Right? And because
Gotcha.
we know that at least one of these is not 0, well, then this side has in fact got to be positive, whereas this side is 0. So we know that we've somehow we've somehow come across we've somehow used a series of logical steps that resulted in something absurd, which means that the original statement has to be not true. It could not have been equal to 0 in the first place. Sorry, let me see if I can make this yeah, I right now I'm not seeing a way to do it other than proof by contradiction, which is a little bit like kind of hard to wrap your brain around if it's like the first couple of times you've seen it. But do you see what I'm getting at here? I'm starting with I want to prove that for any C1, C2 all the way up to Cn, that this is not equal to 0. So in order to this is a little bit hard to prove directly. It's actually not that hard to prove. Okay, you know what? Forget about contradiction, okay? Forget about contradiction. Let me just directly prove that it's not equal to 0. Right? Let me just directly prove that this is not equal to 0. And the way I'm going to do this is I'm going to say if I can prove the square of this thing is not equal to 0, then the regular version of it, the non-squared version, is also not equal to 0, right? Is that fair?
Yeah.
Like x squared is not equal to 0 implies that x is not equal to 0. Is that fair?
Yes.
Gotcha. Okay. So I'm going to prove that this is not equal to 0. And to do that, I'm going to say that, okay, let's examine the square. And this entire thing right here, I'm just taking this thing and squaring it. Right? I'm taking this expression and squaring it. And then in terms where you have like C1 squared, V1 squared, I'm sort of like writing that as a diagonal. This is not a matrix, right? This is just a straight up scalar value. I'm just writing it like an array, like a 2D array, just to sort of visualize it a little bit easily, right? And what I'm telling you is that terms that have a cross term in them, like v2.v1 or v1.v3, those are going to be 0 because that it's orthonormal. Right? The fact that it's orthogonal means that all the cross terms go away. So all that you're left with is this stuff. Right? All that you're left with is C1 squared, V1 squared, C2 squared, V2 squared plus C3 squared, V3 squared, right? And in fact, if we remember that this is orthonormal, which means that Vi squared is equal to 1. Right? Like up here, we said that the magnitude of Vi is equal to 1. Another way of saying that is Vi squared is equal to 1, right? So really, this entire thing is just equal to the sum of all the C1s, C2s, and so on and so forth, right?
Yeah.
And then this is equal to 0 if and only if all of them are equal to 0, right? The only way for this thing to be equal to 0 is when every single Ci is equal to 0. Fair? Because if any of them is that true, right? Yeah, because if any of them are positive or negative, then this thing becomes greater than 0. Because it gets squared.
Right.
And because, right, just like you were saying, this means that the only time that this entire thing is 0 is when all the C's are 0. In fact, I should have said x squared is not equal to 0 if and only if x is not equal to 0. Right? So that this means that we know that this is not equal to 0. The original statement is not equal to 0 uh, if and only if, if and only if the C's are non-trivial. Does that kind of make sense?
Yeah.
Yeah. Sorry, this is a bit of a sloppy explanation on my part, but this is equal to 0 if and only if all the C's are 0, which is exactly the same thing as uh, this is basically saying that um, you know, there does not exist a non-trivial solution. There does not exist a non-trivial solution, right? There does not exist any non-trivial set of C's to make this thing equal to 0. The only way to make this equal to 0 is for the trivial solution, all the C's are 0. Sorry, I'm. It's been a while since I worked in linear algebra, so my phrasing is a little bit poor. But I hope you're sort of seeing the picture. And the fact that we've shown that, uh, right, C1, this linear combination is equal to 0. Um, only for trivial solutions. Well, that's the same thing as saying that this thing has maximum determinant. This is the same thing as saying that. This is the same as saying that it has max rank. The same as saying that it's invertible, etc., etc. Does that make sense?
Yeah.
There were probably other ways to prove this, and maybe I chose a way that's a little bit overcomplicated. But the fact that these are sort of like orthonormal is kind of hinting that all of these are probably going to be independent of each other. And the way I chose to make that proof was by examining the square, the square of this statement. Um, Gosh, it's been so long. I feel like there should be an easier way to prove that. Uh, there should be an easier way to prove that an orthonormal basis should be linearly dependent. Maybe we just quickly Google that. Uh, Show that a uh, orthonormal basis is linearly independent. I've got to be making that. There's got to be a much simpler way to show this. I'm probably just making it stupidly complicated.
I mean, your way worked, so I mean, it's okay.
Dot through by A1. We get okay. Well, they're suggesting that just go ahead and okay. So they're doing the exact same thing. They're rather than squaring it, they're getting three different equations by dotting it through by A1, then dotting it through by A2, and then A3. Right. So yeah, they're doing the exact same thing. Just a bit more directly, right? They're sort of ignoring these components. Where like, do you see how like they end up with C1, uh, C1A squared, like C2 A2 squared, C3 A3 squared? That's basically exactly what I've got down here, right? Just with V's instead of A's. Yeah. But anyways, do you want to talk about this more, or do you want to move on?
I think I'm good on this one.
Okay, gotcha.
Do you know anything about the Graham-Schmidt process?
I was going to mention that one earlier about orthonormal vectors. Um, I always forget it off the top of my head, but
There's
it's
like an
basically some
equation
way to
I just read.
generate new orthonormal vectors, right? Generating a set
Yeah.
of orthonormals.
There was a problem that I was given, and I think I did it right,
Hmm.
but I'm not too sure.
Um,
So I figured
yeah. I don't have a
you
ton of advice for this, other than it's a very procedural set of. It's a very procedural process that you sorry, it's a very procedural process that you're just encouraged to follow, step by step. And computationally, it might be a little bit nasty, but I hope it should be very procedural. You don't have to do a lot of creative thinking. We can take a look at the problem if you like. Feel free to send it. But yeah, the hope for whenever you come up with like a process is that you've got it boiled down to a recipe and don't have to think about it anymore. It looks like you're basically just subtracting out the projections, right?
yeah, it's number 2. Like, so it's like the way he taught us was to like make a vector out of the given ones, right?
Hmm.
And then we apply this uh hello.
The given set is a basis for a subspace. Use the Graham-Schmidt process to produce an orthogonal basis. Gotcha. Okay.
And then I think we're supposed to use something along the lines of this.
Yeah,
So
that looks
that's what
right,
I
right?
did.
So this thing over here is basically just the expression for a projection, right? So yeah, this is totally a mine, and because you're only working in a two-dimensional subspace, this is not so bad. So, like visually, do you understand what you're sort of being asked to do here? Is it's sort of like saying, okay, you're in a three-dimensional space, but you're basically only given two vectors, like maybe this vector, let's say maybe this vector, and like for the sake of simplicity, uh, well, okay, like maybe another vector that has like a z-word component, right? And the idea here is that these two vectors form a two-dimensional span, right? These are
If we
not
can't
supposed to be parallel. This vector is supposed to be in the xy plane, and whereas this vector is supposed to have some z component to it.
tutor
But the
bro, I
idea
can't
is
see
that
what you're
like you can sort of like draw a two-dimensional plane that is the span. It sort of like contains the both vectors. And
tutor bro.
the what's up?
I can't see what you're writing.
I'm sorry. I'm sorry. I'm sorry. Um, I'm sorry. So yeah, I was just drawing like a three dimensional space, and you have two vectors, right? And and these two vectors are going to be they're going to have some span, which I'm sort of drawing as this 2D plane. And this right, the 2D plane is going to contain these two vectors. And the idea is, okay, that's nice, but it'd be really nice if we could, instead of these two like awkward vectors, if we could come up instead with two vectors that happen to be orthogonal to each other. So what the Graham-Schmidt process tells us is like, okay, arbitrarily, let's just choose one of these. So if this is, I think, U1 and U2, right? And we want to find a V1 and V2 that are orthogonal to each other. They're saying, okay, so this is a U. they're saying, okay, well, you may as well let u1 be equal to v1, and then you just have to find v2. Does that make sense?
Yeah.
Yeah. Like, if you're trying to find two orthogonal vectors, well, you can always just start with one of the vectors and then just tweak it a little bit to find an orthogonal one, right? I could have chosen u2 to be I could have chosen u2 to be my final set instead of u1. It's arbitrary. But yeah, the idea here behind the Gram-Schmidt process is to, off the top of my head, uh, I don't exactly remember the justification behind it, but they're basically saying that if you do v2 is equal to u2 minus, what did Wikipedia say? The projection of oh, that's annoying. Oh, they're sorry. They're swapping the U's and V's, which makes my life a little bit annoying. I chose U's for the original vector and V's as my new vectors. They have it the other way around. But that's okay. If we just quickly swap these mentally, I'm going to say V2 is equal to U2 minus the projection of U2 onto V1. What is this actually doing? So let me try to explore a little bit about why this works, right? So can you imagine these two? Let's say that U1 and U2 are not perfectly, um, they're not perfectly parallel or orthogonal to each other, right? They're kind of askew a bit. So maybe they kind of look like this, right? Maybe this one is U1 and this one is U2, right? Can you kind of see that? I'm sort of just redrawing U1 and U2 so that I'm sort of in their plane, so to speak. Does that make sense?
Yeah.
Yeah. So what the Gram-Schmidt process is basically doing is it's saying, okay, let's let this horizontal one be U1. Let's keep that in our final set, right? But then as for our other vector, let's just try to find this vector and call that our V2. Right? So rather than U2, which is kind of at the skew angle, let's figure out this V2. And the way to do this, you can kind of see just by vector addition and subtraction, the critical thing to find is whatever this is, right? And this is precisely the projection, right? This is the projection of U2 onto V1 or U1, because those are basically the same thing, right? Do you see how if we could just figure out what this vector is, we can just take U2 and then subtract out sorry, we can take U2 and then subtract out the projection, and that perfectly leaves us with the orthogonal part. Put another way, if we take U2 and we subtract out the parallel part, that leaves us with the orthogonal part. Do you see that?
Yeah.
Yeah. So that's exactly what the Gram-Schmidt process is. I'm hoping that this sort of visual explanation sort of makes it clear why we have to find the projection in order to get the orthogonal part. Does that make sense?
Does now.
Good. I'm happy that worked. I made this up on the spot. I had to quickly like reverse engineer why the projection was important. Yeah. So like keep in mind U1, right? Maybe U1 and U2 look like this instead. But that's okay, right? The logic is still the same. We still want to find, the sort of like orthogonal part. And to do that, the critical thing to find first is the parallel part, which is just the projection. And then as for like how to find this projection, well, that's exactly the equation that you gave me over here, right? This is just the projection formula that you see all the time in intro multivariable calculus. But yeah, I'm hoping that clears it up. I'm sure you can extend this logic to higher than 2 dimensions. The Gram-Schmidt process probably just keeps something like this going into higher and higher and higher dimensions, right? Actually, I think I figured it out just now. Like, let's say that you had, let's say that you already generated your, you already sort of generated your two. Let's say you were trying to do a 3-dimensional space, and you've already generated your first 2 vectors. And then this other vector that kind of has this, this other vector has an upwards component, but unfortunately it has a bit of skew, so that it has a bit of component in each of these 2 things, right? In this case, you're basically trying to figure out how much it has in common with this vector, how much projection it has into this vector and subtracting that out, and also how much it has, projected onto this vector and subtracting that out as well. And that's exactly what you get from here, right? It's basically just subtracting out, like for V3, for your third angle, it's subtracting out the projection onto one of them and subtracting out the projection onto the other, so that all that you're left with is the orthogonal component at the end of the day. Hopefully that makes sense. Do you buy that?
Yeah. So,
What's up?
okay.
I think you cut out for a moment. Do you buy that?
Hello?
Hey, can you hear me?
Yeah, okay. I think we're good. Yeah.
Yeah.
I think
Reasonably convincing?
yeah.
Okay, good. Was the Gram-Schmidt process just presented in kind of a dry way, where like visually you had no idea what was going on?
Yeah, it was all numbers.
Yeah, it's all numbers, right? It helps a lot if you can just draw one of these things and figure out, like, hey, like this is pretty convincing if you could just see what's happening. But yeah, anything else for me?
Yeah. Have 2 more problems, I think.
Sure, yeah, hit me with whatever you got. Yeah, I like happy to help with, whatever you'd like to take a look at. I always do enjoy this part of my week. Getting to think about just pure math for a little while is such a refreshing break from software.
Different, I
I'm
guess,
sorry?
motivation.
Yeah, I mean, software is just this never-ending grind of just, I have to keep building things. Pure math has a little more elegance to it. Okay, so if U and V is an orthonormal set in V, then little u minus little v is equal to root 2. Do we know what V is? Capital V?
Yeah, sorry. I cut that part off.
Yeah, I assume it's just like R2 maybe? But
Oh wait, no, we just have to verify them.
what's up?
It says that we just have to verify the statements.
Gotcha, but like does it have any definition for what capital V is?
No.
No?
No.
Okay. I mean, I guess it's fine. I just feel like that's
I'm guessing V is like U and V. Like big V is the set UV.
yeah. I guess it's fine. Assuming that V is just any like you know any Euclidean space of at least two dimensions. Where little n is greater than or equal to two. Um, it's just a little sloppy that they don't precisely define, but I don't know. I mean, the way to actually do this is, I think, pretty clear. I hope, but we do know that u dotted with v is equal to 0, right? Because we know that it's orthonormal. Oh, I'm sorry. I need to bring my whiteboard up again. It's like I was saying, Rn for any n greater than or equal to 2. And we know that, u is equal to 1 and v is equal to 1. So this is basically saying that u and v, like, they're basically just, uh, how do we put it? They're basically just two legs of a right triangle, each of length 1, and there's a 90-degree between them, right? And they're basically just asking us, the hypotenuse is going to be u minus v, right? U minus v is the hypotenuse. Um, so they're basically just asking us what is the length of the hypotenuse. And, at this point, we've gone from like the vector world to, fifth grade math world, where if I tell you the lengths of these legs and that it's a right triangle, you can figure out what the hypotenuse is for me, right? That's all this question is
Yeah.
asking.
So we just find that one peak that okay.
Yeah.
It's not
Where
bad.
I guess what's really happening here is, um, sorry, I guess I should draw a little bit more consistently. Really, if you have u minus v, it looks a bit more like riding along u, like starting at the origin, right? Ride along u, and then ride along minus v, right? It's the same. It's the same exact thing, right? It's the same exact thing. The triangle looks pretty much identical, just flipped.
Yeah.
And all the like trigonometry or the Pythagorean theorem is going to be exactly the same. It's just if you want to be technically accurate, this is going to be a slightly better picture than what I had before. But you can see that just use the Pythagorean theorem and get root 2 as your hypotenuse, right?
All right. Not bad. Not bad.
Yeah. Yeah, that's all it's asking. Do you feel like the question kind of worded it in a bit of a scary way? Kind of like obfuscating like how simple it really was?
Yeah, I feel like if I had been given an example like that in lecture, it would have been a little more easier.
Yeah. Yeah. It's one of the hard things I think in intro college math is to not get intimidated by the formalism and whatnot, and to keep in mind what you already do know from before.
There's also a lot of vocab in linear algebra.
Yeah, yeah, there is a lot of vocab.
Maybe the last one.
Sure, you with whatever you like. Ah, Cauchy-Schwartz. Do I even remember what the Cauchy-Schwartz inequality is? It's like one of the most famous and most widely used inequalities. It's just it's just been a while. So the question is, U is equal to AB, V is equal to 1, 1. Use Cauchy-Schwarz to show that A plus B over 2 squared less than equal to A squared plus B squared over 2. So first off, do you know the statement of the Cauchy-Schwarz inequality for vectors?
Like what it means?
Or just like literally the definition.
In my notes, I have dot product of vectors is less than or equal to the product of the lengths of the vectors.
So dot product of the vector, so u dot v, is less than or equal to u squared plus v squared. Is that right?
I think so, yeah.
Oof. Wait, I feel like I'm off by a factor of 2 here.
But
Is there a
don't you
factor
need to
of 2?
put well, like the actual thing is like the I don't know what they're called, the one line bar UV.
Here, let me just look up the statements that we have in mind. This is bad. It's been so long. Um,
Yeah, it's that one.
this one, right? The norm.
Yeah. What are those lines called? The two brackets?
The 2 vertical ones.
Yeah.
Yeah. I just call them. It's just absolute value brackets.
That means like you have to take the magnitude or something. Oh, that's two lines off.
What's up? Yeah, I don't know where I got.
The
Sorry. This is u and v, right? And then it's understood that these like angle brackets u comma v is just the inner product, at least for our purposes of linear algebra. Right, so this is the Cauchy-schwartz inequality. And what I would suggest that we do is to um, something doesn't quite feel right here. Well, the first thing I would suggest is let's just plug it in and see what happens, yeah?
okay.
So if we just go ahead and plug in u dot v, we would get a plus b. Right, that's just u dot v. Less than or equal to the absolute value of u, which is the square root of a squared plus b squared, right? Oh, I'm sorry. My screen is blocked again. You following? Hello?
Am I cutting out? Hello?
Yeah, it looked like it was cutting up a bit there. Can you see my screen right now?
Yeah.
Yeah. So this is the Cauchy-Schwartz inequality, and let's just do the dumbest thing and literally just plug in for u and v, right? So u dot v is just going to be equal to a plus b. That's just our dot product. And then the absolute value, or the norm rather, of u is going to be the square root of a squared plus b squared. And the norm of v is going to be root 2, it looks like, right? The square root of 1 squared plus 1 squared.
Norm means magnitude.
Yeah, basically.
Okay.
The norm of a vector u basically just means the magnitude of u. Yeah. Norm. So, yeah, at this point, it pretty much looks like what we want, right? I would suggest that we maybe just square both sides, because here they have a 2 rather than root 2. So let's just... I feel like I must have copied this wrong, did I? Oh, no, I copied it fine. Basically, let's get rid of these square roots by squaring both sides, yeah? And because this is an absolute value, and this is also positive, squaring both sides should not impact the inequality at all, right? It won't change directions or anything like that. But okay, that gives us a plus b squared is less than or equal to a squared plus b squared times 2. Right?
Yeah.
And at this point, we pretty much already have what they have. We just need to divide through by 2 squared on each side. or 4. 2 squared or 4. So then we can pull the 2 into the parentheses. So this turns into a plus b over 2 squared is less than or equal to a squared plus b squared over 2. Do you see that?
Oh. All right.
Yeah. So that's the example of the Cauchy-Schwartz inequality, but I think maybe it'd be helpful to actually like figure out what the hell these things actually mean.
Yeah.
Right? Like what is the inequality exactly, and when is it a strict inequality and when is it actually equal? And to sort of like view this, we could just think about in maybe just 2 dimensions, right? U and V. Let's take a case where they're perpendicular to each other. So if they're perpendicular to each other, what is U? And let's say that each one has magnitude 1, right? So let's say that they're both, U is equal to V is equal to 1 in this little example. So in this little example, what is U dot V going to be equal to? Given that they're orthogonal to each other.
0.
Yeah,
Right?
yeah, 0. Not a trick question. So, we remind ourselves that, like, I'll say that in just a moment. So U dot V is equal to 0, whereas U is equal to V is equal to 1, so that U times V is also equal to 1, right? So in this case, U dot V is equal to 0, whereas the product of the magnitudes is 1. So yeah, here we have a strict inequality, right? We have 0 is strictly less than 1. Okay. Well, I gave you one example. Can you think of a case where, can you like slightly modify this example so that you would achieve equality? Or, maybe let's give you another example. What if instead of being perfectly orthogonal to each other, now let's say that they're off by 45 degrees. Yeah?
Okay.
If they're off by 45 degrees, we'll have to remind ourselves here. Oh, God. Sine of 45 is 1 over root 2. Right? Because U dot V is just the magnitude of U times the magnitude of V times the sine of 45. Right? Sine of theta, which is the angle between them. That's what this is equal to, right? So it was larger than what it was before when they were orthogonal. But it's still less than the straight up product of the absolute values. And what we find is that as the angle gets closer and closer and closer to approaching each, so that the vectors approach each other, right? Then sine is going to get closer and closer to 1. In which case, like, as we get closer and closer, the equality is going to be achieved. Can you sort of see that?
Yeah.
Yeah, because after all, I'm just going to rewrite it, right? U dot V is equal to U V sine theta. It's the absolute value of sine theta, right? And this is saying that this is going to be less than or equal to U times V. And when you write it this way, the Koshi-Schwartz inequality becomes really obvious, right? Because this is basically just saying that, once you've narrowed it down to this is basically just saying that these two things only like differ by a factor of sine theta. And we know it's true that sine theta is always less than or equal to 1. That's all the Cauchy-Schwartz inequality is saying, right? It's saying that at best, when sine theta, when the two things are sort of parallel to each other, right, equality is achieved. And, that's the biggest that the dot product can get is when the vectors are the same. Otherwise, on the other end of the spectrum, when they're orthogonal to each other, then sine theta is 0, right? That's as small as it can get. That's all Cauchy-Schwartz is saying. You know, it's back in the day where, you know, a simple insight like this would get your name immortalized for hundreds of years.
If only you were back then. They were
Yeah,
back
I
then.
mean, you ever hear of some of these stories of uh like these days it's funny. You have to be like part of a 200-person team at CERN in order to make these big breakthroughs, and back in the day you could just be like a bored aristocrat who would be like, yes, I think I will take 2 hours out of my day to study this noble pursuit of mathematics. And they would just come up with, you know, crazy stuff. Um, Leibniz, the guy who invented calculus at the same time as Newton, apparently was told at age like 22 that his mathematics was subpar, according to his tutor. So the guy apparently just studied incredibly hard for like 2 years and invented calculus, you know, after like 2 years of crunch. It was ridiculous. And then, yeah, like bored nobles back in the day would just come up with crazy stuff. But anyways, that's all Cauchy-Schwartz is really saying. It pops up again and again in more complicated contexts, but at least at the like multivariable calculus or linear algebra level, it's really just saying this very simple statement of, you know, the dot product between the two vectors can at most be equal to the product of the magnitudes. Product of the magnitudes of the vectors. Sound okay?
Good.
Alrighty.
Thank you.
Is that all the questions you had for today?
Just make sure. But yeah, I'm pretty sure that's it.
Alrighty. Let's stop the recording there.